So last session which we did was predominantly focusing on decomposition of services. We talked to two different patterns. One was decomposition using business capability. Second was decomposition using domain-driven design slash subdomain. Both of these patterns help in terms of identification of services in an operation. But apparently, you come to a point where services may not be completely self-contained and they would end up communicating with other services to get their job done. So this is where intercommunication kind of comes in. Intercommunication of services is a fairly important topic and area from a service design standpoint of view or microservice design standpoint of view. And it kind of impacts on some of the non-functional requirements. What are we going to be covering in this session? We're going to be talking to different architecture patterns which are going to be used from an inter-process communication standpoint of view. Largely, they will be around remote procedure invocation, circuit breaker pattern, client-side discovery, self-registration, server-side discovery, third-party registration, asynchronous messaging, transactional outbox, transactional logtailing, and polling publisher. While these patterns will definitely kind of help your thinking in terms of where to end up using these patterns from a design standpoint, we're specifically dealing with inter-process communication. However, there's a more deeper topic because it talks in terms of the importance of intercommunication. How does it really play out specifically from a non-functional requirement standpoint of view? Next area is as services generally have a contract, and this is the ideal, an understanding between the services and client that how they're going to communicate. So when you're evolving APIs, versioning, semantic versioning is an important area as well. Uh, Post that, we kind of talk about the inter-process communications, the trade-offs between the different communication styles. We kind of go on to benefits of using asynchronous messaging. And lastly, we talk about reliably sending messages as a part of database transaction. So before we kind of get deeper, setting the foundation of IPC or inter-process communication, now microservices architecture structures an application as a set of services which may collaborate in order to handle requests. Now these service instances are processed running in different instances, probably container, could be a part of a VM, and eventually they will interact via inter-process communication. Now, multiple IPC exist. The one which is famous, and which has been used in most implementation is REST, and there are other messaging style as well. Choice of IPC is very important when for certain architecture decisions. We'll talk to that. And IPC intersects with transaction management as well because there are situations where one service would actually end up calling another service at the same time. It would want to make an update in database or kind of also have kind of a transaction which kind of runs across two different entities. General rule of thumb, architecture consists of loosely coupled services which communicate with one another via asynchronous messaging and use synchronous protocol to communicate with other applications. Now, first and foremost, we talk to services, kind of talk to other services. Now, largely the interaction style, which kind of we start talking in terms of a service may end up calling one-to-one, maybe exactly calling exactly one service, and each client requests a process exactly by one service. So that's more like a one-to-one communication. Or there could be end up being one-to-many, where each request is processed by multiple services. Now the next dimension which really comes into play is the one-to-one communication or one-to-many communication. Is it really synchronous or asynchronous? Now, synchronous where the client expects a timely response from a service and might even block while it waits. Asynchronous where client doesn't block and the response, if any necessary, isn't necessary, send immediately. So typically, I think it's very clear from the table, the request response is fairly tightly coupled. asynchronous request response, a one-way notification. Then you have the pub sub and publish asynchronous response. We talk to each one of them a little bit more in depth. Starting off with synchronous messaging. Uh, so before kind of getting into synchronous messaging, some bookkeeping activities from a design standpoint of view, which you need to make. So as I kind of talked about, the IDL or the interface definition language, which is the contract between the client and service, that cannot change. And from a design standpoint of view, this is the place from Interprocess where the first starting point where you look at the API first design approach. Obviously, there are going to be message formats when you're exchanging message. Typically, text and binaries. Choice of formats impacts efficiency. Use cross-language message formats to kind of support more than one language. Versioning, as I mentioned, semantic versioning to manage changes better. Obviously, the major, minor, and patch, and eventually the whole idea is to kind of strive towards a backward compatibility change and backward compatible changes are additive changes to API, typically adding optional attributes to the request or attributes to the response and adding new operations. So now kind of going into the service communication more from a synchronous standpoint of view, RPI remote procedure invocation where the client sends a request to the service processes the request and sends back a request response. Now, clients may block waiting for a response, and some may have reacting non-blocking architecture. Typically, what we see in REST and gRPC. Further, now REST has been around for a fairly long time. Obviously, there are certain benefits to it. It's HTTP friendly. Drawbacks typically include challenge of fetching multiple objects in a single request. Uh, the verbs can at times be challenging because in case of supporting more mapping operations besides the verbs which are being given, and it only supports request response. And the most important, the last 2 points are fairly important. Reduce availability because the response side of the service, if it goes down for some reason or unknown reason, it's very difficult to kind of work around problems or design, such as these. And the client must know the URL location. So now gRPC, on the other hand, is a binary-based message protocol. API consists of one or more service, request response message, and can also support streaming RPC. Typically uses protocol buffer, message format in binary. Each field of the protocol buffer is numbered as a type code. A message recipient can extract the field and if it needs and skips the field that it doesn't. So hence kind of working towards a backward compatibility situation. Benefits, straightforward to design API with a rich set of operations, much beyond the standard verbs which are there. Efficient IPC mechanism can handle large messages. Bidirectional streaming enables RPI and message style communication, enables interoperability between clients and services. Now, drawbacks include more work to consume gRPC, not firewall friendly, and both of them typically suffer from partial failure or owing to synchronous messaging. Now, typically the problem with synchronous messaging is, as I talked to earlier, if the service, which is on the response side of the uh, piece of work, kind of goes down, due to failure, maintenance, or overloaded in general, and many clients make same request and consuming service, and eventually, if you're using API gateway, this will lead to failure or unavailability of the API. And this is essential design of the service to play. You need to kind of think in terms of using certain patterns. So circuit breaker pattern is one such pattern which can typically help you in those situations, but this is a partial help. It may not completely help you. So circuit breaker is basically an RPI proxy that immediately rejects invocation for a time period after several consecutive failures exceeds a specific threshold. So we talked about standard implementation of REST, where the API gateway, if unresponsive, will block the client indefinitely, leading to poor experiences. And if it's consumed resources to the thread, and the entire API will not be available. Now, protecting against this, there's certain methods which are available. You can end up using network timeouts, basically, and limit the number of outstanding requests from a client. The last piece is circuit breaker. Track the number of successful failed requests, and if the error rates exceed the threshold trips, the circuit breaker, so further request attempts fails immediately. Now, Netflix Hysterix is one open source library which I've used in the past, which helps implement these patterns. So typically, recovering from an unavailable service, you may return an error code, return a fallback value, in some cases cached value, and as I kind of mentioned earlier, the Hystrix library is really fairly helpful. Now, as you talked earlier, that in a typical request response scenario, the client really needs to know the location of the service. Obviously, not a good design approach. You obviously need to find a way or a mechanism to abstract the service implementation outside of the client. So this is where service discovery really comes in. It's a key component. It's a registry, the database of some sort, which basically has network location and application service instances. Uh, Discovery mechanism updates the service registry when the service instance start and stop. So it's like anything, any of the service instance kind of goes out for some unknown specific or unknown reason, then it kind of it kind of informs the service discovery that, hey, I'm kind of going down. And when the client invokes the service discovery mechanism questions the service registry to obtain a list of available service and routes to one of them. Two main ways to implement service discovery. Services and client interact with a service registry, deployment architecture handle the service discovery. So over and above, there are obviously going to be patterns which are evolving based around the design problems that we see. So kind of uses two patterns: self-registration pattern, where the service registers itself on the registry and supply a health check URL. Client-side discovery pattern, the client queries the service registry to get a list of service instance. Of course, I'm not a fan of the client-side discovery or the self-registration pattern. So this is where the service discovery, kind of comes in the platform at a platform level. So now, while we can argue that the client can obviously ping and find, but why give the work to the client and let everything be done by the platform? So this is where the server-side discovery kind of comes in, server-side discovery pattern comes in. So if you see platform like, Dockers and Kubernetes, they generally have a built-in service registry and discovery mechanism. Deployment service gives each service a DNS name, a VIP, and a DNS name resolves to the VIP. Service registration, discovery, routing are handled completely by the platform. You don't need to kind of bother in terms of those things. And service registry tracks the IP address of the deployed services. So it's the job of the service registry to kind of track if anything were to go down. That's where the health check API comes in. DNS resolves the VIP deployment platform automatically load balances across multiple instances. Now, this kind of gives approaches, ends up using two patterns. So basically, third-party registration, this is instead of the service registering itself with the service registrar, third party called registrar, which typically, as a part of the deployment pattern, hands the registration. So that part where the self-registration is there, it's completely gone out. And then eventually, this is the server-side discovery pattern, which we kind of talking about, where instead of the client querying the service registry, it makes a request to the DNS name, resolves to request router, queries the service registry, and loads a balance and load balances the request. Key benefit of the platform is that all aspects of service discovery is completely handled by the deployment platform. So obviously there are benefits of kind of going with the server-side discovery pattern. Most modern architectures tend to use this and should use this, and you should also consider something of this within your architecture. Moving on to asynchronous messaging. So we talked about synchronous messaging, and we saw request response. We saw issues with the reduced availability on the request response side. Obviously, we need to kind of solve for that problem, and asynchronous messaging is one way to kind of solve the problem. So we talked to that a little bit more. So services communicate asynchronously. Option includes you end up using a message broker, which is the advisable way, which is message-based application acts as the intermediary between the service and client, or go brokerless, such as services directly communicate. Key here is, now we talk about implementing both the request response and the pub sub using the async message background. Now, message broker architecture. So basically, sender writes the message to the channel, receiver reads the message from the channel, Message contains a header, typically a return address, metadata, and a body, text or binary. Types of messages include document, command message, which is equivalent to the RPC request specifies the operations to invoke and the parameters on the server side. Event, a domain event, which indicates a state change of a domain object. Message channel, messages are exchanged over channel. A business logic in the sender invokes a sending port interface, which encapsulate the underlying communication mechanisms. Sending port is implemented by the message sender adapter class, which sends the message to the receiver via message channel. The message channel is an abstraction of the messaging infrastructure. Message handler adapter class in the receiver is invoked to handle the message. It invokes the receiver port interface implemented by the consumer business logic. Any number of senders can send message and any number of receivers can receive message over channel. Of course, you don't really need to get into the specifics of the message channel, but that's just to kind of give you an idea. I mean, most of this is being managed by, we have ready-made code-based libraries to kind of do this. What's the walk away from the slide is you need to understand the two kinds of channel, point-to-point and pops up. Now, next kind of let's get on to how to really implement the request response and a message broker scenario. So message inherit in the asynchronous in the case continues to block till it receives a response. Now the client and service implement an asynchronous response style interaction by exchanging a pair of messages. Client sends a message, client sends a command message, specifies the operation to be performed, the parameters to a point-to-point messaging channel owned by the service. Service process the request and sends a reply in which contains the outcome to point channel which is owned. So this is pretty straightforward implementation, not much to talk. And eventually we kind of get into the pub sub and the pub sub asynchronous, publish asynchronous. So services uses PubSub to publish domain, which represents changes at the domain event level. Services then publish the domain event, which is owned by the channel, which services own the channel. Service that's interested in the domain event, which eventually kind of subscribe to the channel and subscribe. A message will have built-in support for PubSub interaction style. Client publishes a message to pub channel that is read by multiple consumer. Now, publish asynchronous is more or less a high-level interaction implemented combining PubSub and a request response. Now, client publishes a message that specifies a reply channel header to the PubSub. Consumer writes the reply message and with a correlation ID. Client gathers the response by using a correlation ID to match the reply message with the request. So before we kind of get a little deeper into the async style, I mean, there's a place where I would want to make a mention of the documentation which is required from a interprocess communication standpoint of view. And you will need to document the async operation. So everything from message channel, message type, exchange over the channel and the formats. Response async style consists of service command, message channel, types, formats, and command message that services accept and the type, the format, the reply message sent by the service. Similarly, one-way notification. And obviously, there's a mention about documenting publishing event because any events which the domain level events which kind of also are important. So services can publish events using PubSub interaction style which will consist of event channel types, format, and the event message published to the channel. So these are things which are important from a documentation standpoint of view. Furthermore, messaging option. Now, I want to do a quick comparison between brokerless and broker-based message. So brokerless message is pretty much straightforward. There's no intermediary in between. Services have exchanges. I can exchange directly. So ZeroMQ is a popular brokerless messaging technology. Now, support a variety of transport protocols, TCP, Unix, style, domain sockets, and multicast. Benefits include lighter network traffic, better latency, eliminates possibility of a message broker being a performance bottleneck or a single point of failure. I mean, that's an important piece which I think kind of works against the message broker-based architecture, but there are ways to solve the problem. Features less operational complexity as there is no message broker. It's kind of centered around, message broker-based deficiencies. Drawbacks: service needs to know each other's location, offers reduced availability. Implementing mechanisms such as a guaranteed delivery is more challenging. Now, broker-based messaging typically now message broker is an intermediary. It's a sense a sender writes a message to the broker, which in turn delivers it to the receiver. Sender does not need to know the location of the receiver. A message broker buffers a message until the consumer has been processed. So there's, in a way, kind of guaranteed delivery. SLAs can be met out here. Typical message brokers, which we talk to, is ActiveMQ, RabbitMQ, and Apache Kafka. Factors to consider when selecting a message broker include support languages, message standard, message ordering, delivery guarantees, persistence, durability, scalability, latency, competing consumers. Benefits includes loose coupling, message buffering, flexible communication, explicit inter-process communication. Drawbacks, obviously we talked about performance, potential performance bottleneck, because it kind of single point of failure, additional operational complexity. Point of consideration from a message broker standpoint, of course, this is more from a channel perspective, but it's important to know, uh, the channel concept is implemented differently in each and every message broker implementations. For JMS, the point-to-point channel is queue. PubSub, it's more of a topic. Kafka is topic, and AMQ will be an exchange plus queue and a fan-out message exchange and a queue over a consumer. AWS Kinesis will be mostly streamed across two, and AWS SQS will be queued. So this is just to kind of understand that there are going to be implementation level changes, which kind of comes in because the underlying construct which supports the channel or point-to-point and PubSub channel are, which will vary. Furthermore, transactional messaging. Now, there would be a situation where a service which is calling another service at the same time may want to update a database. So services often need to publish messages as a part of transaction and updates a database as a part of other resources. Both database update and sending message should happen with the transaction. Traditional solution for distributed transaction spans messages, message broker, and database aren't a good choice. I mean, I know the ancient and old stuff which is available, but probably it's not good. Separate session is going to be there. We're going to cover and we're going to have a separate session which is covering distributed transaction more in detail. We talk about saga patterns and so on. But some of the options listed below: using a database table as a message queue, publishing event using a polling publishing publish pattern, publish event by applying transactional log tailing pattern. We'll talk to this a little bit in detail in the next session. Uh, Obviously, the last walkaway is that tend to use asynchronous messages as far as possible, or you may want to kind of move the request response to a message broker architecture, but still kind of give you a little bit of asynchronous flavor to the architecture. And the replicate data service maintains a replica of the data. This is another method in terms of by subscribing events published or implement one of the async patterns to achieve the same. That being said, the session kind of comes to an end, and what are we walking over the session? We talked about interprocess communication is the play which you really need to be cognizant when you're designing services, when it comes to communicating services. Need to make sure they are backward compatible. The APIs services should ideally communicate asynchronous wherever possible. It's not a ground rule of thumb to kind of go with that, but there would be situations for synchronous implementation, try to use the Netflix hysterics, or build your own circuit breaker pattern and kind of use that. Architecture that uses synchronous communication is best to use service discovery mechanisms implemented by deployment platform, server-side discovery and third-party registration pattern. Good way to design message-based architecture is to use message and channel mode, which extracts the details of the underlying message. That being said, thank you for the session and hope this session was helpful for you. If there are any comments or recommendation in terms of how I would want to conduct this session a little differently, please feel free to reach me out at asolanki77 at gmail.com. Thank you very much.